So for the next section, we're just going to do an example. I found that students get more confused if I give definitions of all this stuff. I just kind of want you to understand what's happening. So in this example, we are going to determine where the function is increasing, decreasing, or constant. Then we're going to find all local minima and maxima. And when we're increasing and decreasing, what we're going to do is we are going to look from left to right. And so what's going to happen is we are going to determine the x values where it's increasing and decreasing. If you have no idea what I'm talking about, we'll talk about it. So let's start with increasing. So increasing, what we're going to do is we're going to look on the graph from left to right, see where the function is going up. So my function right here is going up from starting at -3, x equals -3. It is then going to keep on going. It doesn't actually stop increasing at -2. It keeps going and going and going until x equals 0. So that's where it's increasing. And so the intervals of increasing are going to be from -3 to 0. That's the first one. It also is going to happen right here. This point, by the way, is 2, 1. I forgot to write it down. It's going to happen from x equals 2 to x equals 3. And finally, it happens at the very end from 5 to 7. These are my intervals of increasing. By the way, whether you use either brackets or parentheses just kind of depends on your textbook. Your textbook uses brackets, so I'm going to use them here, but I've seen a lot of other pre-calculus books that use parentheses. In AP Calculus, they really don't care very much, so you can use either brackets or parentheses. That's fine. So let's go ahead and see if you could figure out on your own where it's decreasing. Please pause the video and try it. So this function is decreasing at this part right here and that part right there. So the first interval, remember we're going to use the x values, starts at x equals -4 and it ends at x equals -3. The second interval starts at x equals 0 and ends at x equals 2. The final thing I asked you to look at is where the function is constant. That happens right here when I have a straight horizontal line, and that's going to be from +3 to +5. So the second thing we're going to be looking at are local minima and maxima. And you might be wondering, what the heck is a minima or a maxima? That's just the plural of the word minimum and maximum. So we're going to look at our graph and look at all of our peaks and valleys. Those are going to be where our minimum and maximum values are. So here at -3, 1, I have a local minimum. And the answer for like the question, where is the local minimum? We would use the y value, which is -1. Sometimes you're going to be asked, like, is there a minimum at 2? And then you would say yes, because that's when that means that x equals 2. So there's a minimum at x equals 2, but the actual minimum value is 1. By the way, there's just a random dot there. It's not supposed to be 0.1. It's actually just 1. So if you were looking at that confused, sorry about that. So then the local maximum values are going to be your peaks that you have. So I have a local max, and it equals 3. And that's actually technically the only local maximum. Those areas where the graph is constant, we're not going to worry about those. So the one other thing I want to mention in this video is an absolute minimum and an absolute maximum. So actually right here, the lowest value on the entire graph is this one right here. So in addition to being a local minimum, this is also an absolute minimum. And it's at -1. It's equal to -1. The other local min, it's not an absolute. The other thing is we have this local max right here at -3. That is not my absolute maximum because my endpoint actually has a higher value. So I actually have a maximum here when x is 7. My maximum, my absolute max, is going to be 3.5. So the last thing I want to give you in this video is the extreme value theorem. The extreme value theorem says that if x is a continuous function, then f has an absolute minimum and an absolute maximum on AB. And so basically what it means, I'll show you something. So we have two types of, and actually the key thing is whose domain is a closed interval. So I'll give you an example of a function that has a domain that's a closed interval. If you have something like this, that means that that function has a beginning and an end. That you can see that there's absolute minimum, there's an absolute maximum. The minimum is right here, the maximum is right there. Sometimes they're at the end point. So, sorry, I used a lot of abbreviations. Sometimes you're going to have something that kind of goes on forever. This one, for example, this is well, it's supposed to be a line, but it doesn't actually look like one. That one is not on a closed interval. You might be able to notice that actually that one has no absolute max or min. That being said, sometimes things that are continuous and are infinite will have an absolute max and absolute min or both. So like, for example, if I have this parabola right here, that one has an absolute minimum but no max. So you will have cases where things do have an absolute minimum and maximum. So it doesn't necessarily have to have the domain of a closed interval. But if it does have a domain that's a closed interval, then it has an absolute maximum minimum. That's what this theorem is saying. We're not really going to spend much time on this theorem. I just kind of wanted you to see this because next year when you get to calculus, we do have quite a few theorems that you're going to have to look at.